So guys, this recording is going to belong to your third week of online classes, which is going to be the next Saturday. So, as we concluded with the department, the decision is that we're going to have the recording of the classes sent to you before the class is conducted, and you have to watch it on your own. Uh, and if you feel you have questions, you have to write down your questions and ask it when we meet online. So our online sessions are going to be dedicated to Q&A sessions. Okay, are going to be dedicated to question and answer, and the actual lectures are going to be presented in this format. Now, in the previous part, we covered everything except for the examples of Note 3. So we start by doing that, and after that, we're going to move to the other subjects. Now, at the end of the previous lecture, we generalized the concept of linearization and the concept of total differentials for functions of more than two variables. Now, example 9 is an example on that. Here we have a function of three variables, f of x, y, and z equal to x2 minus xy plus 3 sine of z, and we have to find its linearization at point 2, 1, and 0. Now, first we have to calculate the actual value of the function at the point f at 2, 1, and 0, which is 2 to the 2 minus 2 times 1 plus 3 times sine of 0, which is 2. Then we have to evaluate round f over round x at point 210, which is 2x minus y at 2y and 2, 1, and 0, which is 3. Then we need to calculate round f over round y at the point, which is the evaluation of minus x at point 2, 1, and 0, which is minus 2. And round f over round z, which is 3 times cosine of z, evaluated at the point, is going to give us 3, because cosine of 0 is equal to 1. So we can conclude that the linearization would be 2 times 2 plus 3 times x minus x0, which is 2, minus 2 times y minus y0, which is 1, plus 3 times z minus z0, which is 0. So after simplifications, we reach to this. 3x minus 2y plus 3z minus 2. It is good practice to do an exercise just like what we did in the first linearization example on your own. You can consider a point very close to the point 210, for example 2.01, 1.01, 0.01, and see that what is the difference between the linearization of f equal to this at that point and the actual value of the function f at that point. Now, example 10 is an example on the generalization of the concept of total differential. Okay? And sensitivity analysis for a function of more than two variables. Now, the function in this example is actually a formula that is very common in commerce and economics. Now, example 10 is titled the Wilson lot size formula. The formula that I'm talking about is called the Wilson lot size formula. Now, the Wilson lot size formula in economic says that the most economical quantity Q of goods, radios, shoes, rooms, whatever, for a store to order is given by the formula Q equal to a square root of 2km over H, where K is the cost of placing the order, M is the number of items sold per week, and H is the weekly holding cost for each item. Cost of capacity, cost of space, utilities, security, etc., etc. To which one of the variables K, M, and H is Q most sensitive near the point 20 to 20 and 0.05, and give reasons for your answer. Now, we have to start by the total differential formula for the function Q of Km and H equal to a square root of 2Km over H, and evaluate the coefficients at the given point and see which variable has the biggest coefficient, right? Now, if Q is equal to that, then dq is equal to rho Q over rho K times dk plus rho Q over rho M times dm plus rho Q over rho H times dH. Now, if you calculate rho Q over rho K, you're going to reach to this. You have to do it at home on your own. If you calculate rho Q over rho M, you're going to reach to this. If you calculate rho Q over rho H, you're going to reach to this. You have to make sure that all these results are correct. Now, if we factorize 2km over h power minus 1 over 2, which is common between all these coefficients, we're gonna reach to this, right? Now, if we evaluate dq at the given point to 20, 0.05, meaning k equal to 2, m equal to 20, and h equal to 0.05, we're going to reach to this. And after simplifications, we're going to get 10 times dk plus dm minus 400 times dh. And what is the interpretation of this conclusion? It is that Q is the most sensitive to H because the absolute value of the coefficient of H is the biggest. So after H, Q is most sensitive to K, and after that to M, right? Okay, this is the end of the solution to example 10 and end of note 3. So guys, now let's go to note 4. In this note and note 5, the subject of discussion is the multiple integrals. Now, in the previous notes 1 to 3, we learned a couple of things for multivariable functions. And the first one was how to calculate the partial derivative for these multivariable functions. And the next one was how to calculate the directional derivative for these functions. Then, using the concept of tangential planes and tangential and normal lines. We learned how to linearize functions of more than one variable. Now, in this note and the next one, we're going to learn how to calculate the integrals for these multivariable functions. So, let's go to the second page of note 4. Now, first we try to learn to calculate the integration of a multivariable function under the title of double integrals. Now, in the previous semesters, we defined the definite integral of a continuous single variable function over an interval from a to b, as you remember, as a limit of a summation which we called the Riemann sum. Now, in this section, we extend this idea to define the double integral of a continuous function of two variables, f of x and y, over a bounded region, which is a rectangular region which we call R in the xy plane, and in both cases, meaning for a single variable function and a multivariable function, the integrals are defined as limits of approximating Riemann sums. Now, you have seen uh, this process for a single variable function in the previous semesters, and we're going to give you a reminder of that here. But for a multivariable function, this process is our new subject of discussion after you get your reminder of the definition of definite integral for a single variable function. Okay, so let's go. Now, a review of the definite integrals which we saw in the previous semesters. Now, when we derived the definition of the definite integrals, we first thought of this as an area problem. We first asked, what is the area under the curve? And to calculate this area, we broke up the interval from A to B into n subintervals of width equal to delta x. Then we chose a point xi star from each interval as shown below. Then for each of these rectangles, the height was f of xi star, and we could then use the area of each of these rectangles to approximate the area as you see in this equation here. We said that the area under the curve is approximately equal to this, f of x1 star delta x plus f of x2 star delta x plus this in the same way till the nth interval. Now, then we said to get the exact area, we then take the limit as n goes to infinity. And this was also the definition of the definite integral. So, A meaning the area, the exact area under the curve was equal to the limit of that sum which we called the Riemann sum, and that gave us the definition of the definite integrals. Now, for a multivariable function, the process is the same. Now, we want to integrate a function of two variables, f of x and y. Besides having a double variable function, we assume that we are integrating over a region instead of an interval. We will integrate over a region of R2. R2 is the same as the xy plane, okay? And we are integrating our double variable function f of x and y over a region of R2. What do we mean by that? With functions of one variable, we integrated over an interval, which is a one-dimensional space. Now, for function for a function of two variables, it makes sense to do the integration over a two-dimensional space, which we call a region. Okay? Now, let us start out by assuming that the region in R2 is a rectangle, which we will denote as this. So R equal to interval from A to B times the interval from C to D is how we denote a rectangle in the xy plane. Now, this the first interval in this shows you the range for x, and the second interval in this shows you the range for y. Now, if you look at this figure, this is how we show this rectangle in the xy plane with this notation. Okay? When x changes from A to B and y changes from C to D, we're going to have a rectangular region in the xy plane, which we can show with this notation, r equal to interval from A to B times the interval from C to D. Okay? We will also initially assume that our double variable function f of x and y is positive, just for the sake of simplicity and getting a clearer understanding, although this doesn't really have to be the case. Then let's start out with the graph of the surface S given by graphing f of x and y over the rectangle R, as you see in this figure here. So this surface S in purple that you see here is the graph of f of x and y over the rectangle R. Okay? Now let's ask, what is the volume of the region under S and above this plane R? What is the volume of this region that on one side has S and on the other side has R? Okay? This is the question we are trying to answer. Just like for a one variable function, we try to answer what is the net area under the curve. Now we are asking what is the volume of the region under the surface. Okay? Now, we will approximate this volume just like what we approximated the area under the curve. We will first divide up the interval from A to B into n subintervals, and then divide up the interval from C to D into M subintervals, and this will divide up R into a series of smaller rectangles, right? And from each of these smaller rectangles, we will choose a point xi star, yj star, and go on from there. Go on from there. So this is what we do first. We divide up the x side into n subintervals. Then we divide up the y side into m subintervals. And from each of the smaller rectangles that is created, we're going to choose a point which we call xi star, yj star. And here is a SketchUp of this setup. We have divided up the x side, which was from A to B, into n subintervals. Then we have divided up this y side, which was from C to D, into m subintervals. And now the region R is divided into m times n smaller rectangles, which you see here. And from each of these smaller rectangles, we choose a point which we call xi star, yj star, where I is from 1 to n and j is from 1 to n. Okay? This is how we divide up this rectangular region R into a number of smaller subintervals, subrectangles. Now, over each of these smaller rectangles, we will construct a box whose height is given by f of xi star by j star. Here is a sketch of that, right? This is our surface S. This is our region R. Now, these boxes are built up with the base equal to each of those smaller rectangles and the height equal to f of xi star yj star. Okay? Now, each of the rectangles in the division of R had a base area of delta A, and the height of each of these boxes is f of xi star yj star. Okay? So the volume of each of these boxes is f of xi star yj star times delta A. Now, the volume under the surface S is going to be approximately equal to this double sigma, which is what? Which is the summation of the volumes of all these boxes that you see here. Here we have a double sum because we will need to add up volumes in both x and y directions, right? We had n subintervals in the x direction, so we have a sigma with I changing from 1 to n, and we had m subintervals in the y direction, so we have a sigma with j changing from 1 to m. In this way, you're gonna get the summation of the volumes of all these boxes that you have in the figure of page 4, right? Now, the volume under the surface S is approximated by this double sigma. Now, to get a better estimation of the volume, we will take N and M larger and larger, and to get the exact volume, we will need to take the limit as both N and M go to infinity. So, the limit of this double sigma when N and M both go to infinity is going to give you the exact volume under the surface S, which we're going to call what? We're going to call the double integral of the double variable function f of x and y over the region R. So the exact value of the volume under the surface S is equal to the limit of this double sigma when N and M both go to infinity. And this setup should look familiar. This looks a lot like the definition of the integral of a function of a single variable. In fact, this is also the definition of a double integral, or more exactly, an integral of a function of two variables over a rectangle. So, the official definition of a double integral of a function of two variables over a rectangle are, as well as the notation we use for it, is this. V, which is the volume beneath the surface S, is shown by the double integral of the double variable function over the region R, and by definition it is equal to the limit of this double sigma when N and M go to infinity. Now, I want you to notice the similarities and differences between the notation that we have for a double integral and the notation that we used to have for a single integral. Here, instead of one integration sign, we have two integration signs. And we do this to denote the fact that we are dealing with a two-dimensional region. Okay? And we have a differential here also. And note that the differential is dA instead of dx or dy. Okay? And also notice that here we don't have limits on the integral signs. Okay? Instead of the limits for the integral signs, we have the r written below the two integrals to denote the region that we are integrating over. Okay? Now, we can use this double sum in the definition to estimate the value of a double integral if we need to. If we choose xi star and yj star to be the midpoint of each of the smaller rectangles, then the estimation that we get for the volume between the surface and the region R is going to be called the estimation derived by the midpoint rule. Okay, and if we decide to do that, instead of writing xi star and yj star, we write xi bar and yj bar. Okay, now example 1 is an application of the midpoint rule. It says use the midpoint rule to estimate the volume under the function f of x and y equal to x2 plus y and above the rectangle given by x between -1 and 3 and y between 0 and 4 in the xy plane. And it says that we have to use 4 subdivisions in the x direction and 2 subdivisions in the y direction. Okay, so the function is given to us, the rectangle is also given to us, the number of subdivisions in the x and y directions is also given to us, and we want to use the midpoint rule to estimate the volume under the surface. And the meaning of using the midpoint rule here is to choose the midpoint of each of the smaller rectangles in order to do the estimation. So let us get on to the solution. Let's first get a quick sketch of the rectangle we are dealing with, and this figure at the end of page 5 is going to give you the sketch. X changes from -1 to 3, y changes from 0 to 4, and this is the rectangle that you have. We are supposed to have 4 subdivisions in the x direction, as you see, and 2 subdivisions in the y direction, as you see. So each of the smaller rectangles have a width equal to 1 and a length equal to 2. So dA for each of these smaller rectangles is going to be equal to 2. Now, using the midpoint rule means choosing xi star and yj star as the midpoint of each of these smaller rectangles, as we've done. These points that you see in bold black are the midpoints of these smaller rectangles. Now, the coordinates for these points is very easy to acquire. For this midpoint, the coordinates are -1/2 and 1. For this one, you have 1/2 and 1. For this one, you have 3/2 and 1. For this one, you have 5/2 and 1. For this one, you have -1/2 and 3. For this one, you have 1/2 and 3, 3/2 and 3, 5/2 and 3. And the coordinates of these midpoints are given here. These are just what I announced when we were looking at the picture. Now, in order to estimate the volume under the surface, now we have to just calculate the value of this double sigma. Okay? Now, this xi bar and yj bar in the formula are simply the midpoints of each of the blocks, and dA is the area of each of the blocks. And as we said, delta A or dA is supposed to be 2. Now, we also have to evaluate f, which is equal to x2 plus y, at each of these xi hat, yj hat values. Now, because delta A is equal to 2, that double summation turns out to be equal to this. This is the same summation, only we've replaced the delta A with 2. Now, the best way to compute this double summation is to first compute the inner summation for each value of I. Okay? So for I equal to 1, we calculate sigma j from 1 to 2 times f of x1 hat, x1 bar, yj bar. For I equal to 2, we calculate sigma j from 1 to 2 times f of x2 bar, yj bar, and so on. And these calculations are done here. For I equal to 1, we've calculated the inner sigma, which was sigma j from 1 to 2 times f of x1 bar, yj bar, which is sigma j from 1 to 2 times f at x1 bar was what? x1 bar was minus 1 over 2. 2 times f of minus 1 over 2 yj bar. y1 bar is equal to 1, y2 bar is equal to 3, y1 bar is equal to 1, y2 bar is equal to 3. So the value of this sigma is equal to 2 times f at minus 1 over 2, 1 plus f at minus 1 over 2, 3, which is 9. For I equal to 2, we go through the same process, and we're going to get 9 in the end. For I equal to 3, we're going to go through the same process, and we're going to get 17 in the end. For I equal to 4, we're going to go through the same process, and we're going to get 33 in the end. And we can now compute the outer summation, and this is just the sum of all the inner summations we computed. So the volume is approximately equal to this b, which is equal to this double integral, is approximated by the midpoint rule by the value of this double summation, which is equal to 9 plus 9 plus 7 plus 17 plus 33, which is 68. Now, after we learn how to calculate the value of this double integral, and when we learned how to do that, we're gonna see that the value of this double integral is exactly equal to 208 over 3, which is 69.33. So the exact value, as we're going to learn in the future, will be 69.33, and the value of the approximation that we made here using the midpoint rule was 68. So we see that the midpoint rule gave us a very good approximation with a small value, a small error value, and the approximation was a fairly close approximation. Now, in the next section, we're gonna learn how to actually calculate the value of a double integral without using the definition and using the theorems that are available. Now, in the previous section, we gave the definition of a double integral. However, just like with the definition of a single integral, the definition is very difficult to use in practice. So we need to start looking into how we actually compute double integrals. Now, continuing this section, we will assume that we'll continue to assume that the region is rectangular with x from a to b and y from c to d. And we will look at more general regions in the next section. Now, the good news is that this following theorem tells us how to compute a double integral over a rectangle. And this theorem is called the Fubini's theorem. And it says if f of x and y is continuous on the rectangle R from with x from a to b and y from c to d, then the double integral of f over R is equal to the integration from a to b of the integration from c to d of f of x and y, and that is equal to the integration from c to d of the integration from a to b of f of x and y. Now, we're going to reach to what does this mean in a minute. For the moment, know that these integrals that now have lower limits and upper limits are called iterated integrals. Iterated integrals. Now, so what do these iterated integrals mean? We're going to get to that in a second. Note that there are in fact two ways of computing a double integral over a rectangle, right? We can calculate the double integral in this way or in this way. For every double integral over a rectangular region, that is true. There are two ways to calculate the double integral. And look at the screen carefully. This integral, the first integral that you write here, is called the outer integral. And the second integral that you write here is called the inner integral. Okay? And this first differential that you write here is called the inner differential, and this second differential that you write here is called the outer differential. Okay? So, outer integral, the first one, inner integral, the second one, inner differential, the first one, outer differential, the second one. Now, notice that the limits for the outer differential matches the limits for the outer integral matches the outer differential, and the limits for the inner integral matches the inner differential. Okay? What did we say? We said that the limits for the outer integral matches the outer differential. The limits for this matches this, meaning that the limits for this outer integral should be the limits that we have for x, which is from a to b, and the limits for this inner integral should match this inner differential. So the limits for this inner integral should be the limits for y, which is from c to d. Now, if we decide to write it in reverse, so if the outer integral has the limits from c to d, then the outer differential should be dy, because c and d are the limits for y. And if the inner integral has the limits a and b, then the inner differential has to be dx. Okay? So, in other words, if the differential that you have in your double integral is dy dx, then the outer differential should have the limits for, sorry, the outer integral should have the limits for x, and the inner integral should have the limits for y, as we see here. And if the differential that you decide to write is dx dy, then the outer integral should have the limits for y, which is from c to d, and the inner integral should have the limits for x, which is from a to b. Okay? Now, these are all pieces of knowledge. We haven't yet understood how to actually calculate these iterated integrals. Okay? We haven't yet learned how to calculate these. That is our next subject of discussion. So, let me tell you again that if the inner differential is dy, then the limits on the inner integral must be the y limits. And if the inner differential is dx, then the limits on the inner integral should be the x limits. Okay? Now, suppose that we want to calculate that double integral that we had using the first possibility, meaning writing the differential as dy dx. Then let me tell you that this double integral is actually equal to the integration from a to b of the integration from c to d of f of x and y dy, right? This is super duper important. Now, what does that mean? It means that we can treat these iterated integrals as two simple integrals. This, the integration from a to b, integration from c to d of f of x and y dy dx is actually equal to the integration from a to b dx of this integration, and the integration from c to d of the integration from a to b of f of x dx dy is can be treated like this. We assume that we have an integration from C to D with dy, and we have to calculate the value of this inner integration, calculate the result, and then calculate the result of this outer integration. Okay? So there is an invisible parenthesis in the notation for double integrals, in the iterated integrals. Now, let me tell you again, the double integral of f of x and y over the region R, when R is a region in which x changes from a to b and y changes from c to d, is equal to the value of this iterated integral, and the iterated integral can be interpreted as the integration of an integration. Okay? Our job is to first calculate the value of this inner integral. After we found out the result, we're going to write it and then calculate the value of this outer integral. But the point is that the value of this inner integral is going to be a function of x when you write it in the form of integration from c to d of f of x and y dy. The result of this integration in which y changes is going to be a function of x, as you're going to see in the examples. And the result is going to be the integrand of this integral, this bigger integral, that for which x is the variable. So we will compute the double integral by first computing integration from c to d of f of x and y dy, and we compute this by holding x constant and integrating with respect to y as if this were a single integral. Okay, so when we want to do, please pay careful attention, when we want to calculate the value of this inner integration, and we're writing integration from c to d of f of x and y dy. When y is changing, we treat x as a constant. If we used the other notation and we were calculating the integration from a to b of f of x and y dx, then we would consider y as a constant. Now, in this integral, so please pay careful attention, I'm repeating myself. In this integral, integration from c to d of f of x and y dy, when y is changing and we have dy, we treat x as a constant. If it was dx and x was changing, we would treat y as a constant. Okay? This is very, very much similar to what we had in the partial derivatives, right? Over there, when we had round over round x, we treated y as a constant, and when we had round over round y, we treated x as a constant, Now, here in the integration, when we have dy, we treat x as a constant, and when we have dx, we treat y as a constant. Okay? So, let us go to the examples. It says compute each of the following double integrals over over the indicated rectangles. The In the case A, the function is 6xy2, and the indicated rectangle is R with x changing from 2 to 4 and y changing from 1 to 2, right? Now, as we learned in the Fubini's theorem, we can calculate the value of this double integral in two ways. The first way of solving that is written here in solution 1, and in the second way of calculating that integral is written here in solution 2. Now, it doesn't matter which variable we integrate with respect to first, we will get the same answer regardless of the order of integration. To prove this, let's try both cases to make sure that we get the same answer. Now, in the first solution, we are integrating with respect to y first. What does that mean? It means two things. The differential is dy dx, and the limits that we write for the integrals. First, we have to write the limit for x, then we have to write the limit for y. Okay? Now, let us continue. This iterated integral is equal to the integral of the inner integral. Okay? So, integration from 2 to 4, integration from 1 to 2 of 6xy2 dy dx is equal to the integration from 2 to 4, and here we have dx of the integration from 1 to 2 of 6xy2 dy, right? 6xy2 dy. We have to first calculate the result of this integration in the brackets, and then we have to calculate the result of the outer integral. The result of the integration in the brackets is what? We want to calculate the integration of 6xy2 dy. Y is changing, so we treat x as a constant. Okay? So what do we have? We have 6x, which is a constant, times the integration of y2, which is y3 over 3, right? 6x times y3 over 3 is 2x y3. Okay? And we have to evaluate this 2x y3 at 2 and 1, because y was changing between 1 and 2. Okay? So we're going to get 2x times 2 to the 3 minus 1 to the 3, which is 14x. And now that we have found the result of this inner integral, which was an integration with respect to y, we are able to calculate the result of the outer integral, which is the integration from 2 to 4 of 14x dx. And that is a very simple integral to calculate, which is 7x2 and 2 and 4, which is 7 times 4 to the 2 minus 2 to the 2, which is 7 times 12, which is 84. Very well. Now, in the second solution, what are we going to do? We're going to first calculate the integral with respect to x. So, in the second solution, our inner integration is going to be the integration with respect to x. Here, our inner integration is the integration with respect to x. So, if you write it like this, and we decide to integrate with respect to x first, outside we're going to have dy and y changes from 1 to 2. We have to be careful about setting up the correct lower and upper limits for each of the integrations. Now, calculating this one, the integration of 6x by 2, then we are calculating the integral with respect to x. In order to do that, we have to consider y to be a constant. So 6y2, we're going to consider it to be a constant. We have only one x to integrate, and it is x2 over 2. 6y2 times x2 over 2 is equal to 3x2y2, right? And if you consider the lower and upper limits, we're going to have 3y2 times 4 to the 2 minus 2 to the 2, which is 36y2, right? Now, the outer integration is the integration from 1 to 2 of 36y2 dy, which is a very simple integral, which is 12y to the 3, y changing from 1 to 2, which is 12 times 2 to the 3 minus 1 to the 3, which is 7 times 12, which is 84, right? So you see that the result of the calculation, no matter which integration we choose to do first, is going to be the same. Here also we got 84, right? So in the first solution, the inner integral was the integration with respect to y, and the outer integral was the integration with respect to x. And in the second way, the inner integral was the integration with respect to x, and the outer integral was the integration with respect to y. Okay, that is it for this week. I'm waiting for your questions in the Q&A session that we're gonna have. Thank you guys very much. See you next week.